All right, latch up. Let's welcome Akash.
All right, thank you, everyone. I'm going to be talking about static timing analysis today. So who here has used a static timing analysis tool before? Raise your hand. Cool. Nice. And who here has used an open source static timing analysis tool, such as OpenSTA or one of the other ones? OK, few hands. And who here knows how a static timing analysis tool works? OK, a few people. Great. So I'm gonna give sort of a primer on STA from first principles, talking about how it works. I'm going to talk about, so what it is. And oops, I skipped all of the. Yeah, so the basic concepts. I'm going to talk about the open source standards that exist, so Synopsys Design Constraints, and then also going to talk about the Liberty standard and go into a little bit about how how delays are calculated inside of a static timing analysis tool. Finally, at the end, I'll go and talk about OpenSTA, which is an open source implementation of all the above, and talk about some recent progress in static timing there. OK, so what is static timing analysis, and why do we need it? So the idea is that you want to statically analyze a digital circuit that you have to calculate what is the maximum clock frequency I can run this circuit at. You want to be able to prevent problems that can happen, such as metastability and capturing the wrong signals at your flops. Be able to find what are the critical paths inside of the design, so which paths should be the ones that you worry the most about, right? And then finally define timing interfaces to other blocks and have people be able to use your blocks and understand when the signals should be expected to arrive there. And one of the great parts about doing static timing analysis, so the reason it's static, is that you don't actually need any simulation vectors in order to validate the timing behavior. So the first thing to think about is our combinational timing arcs. So in a typical digital circuit, you'll have standard cells and logic gates, and these will have timing arcs associated with them, which are arcs between the input ports of the cell and the output ports. So for an AND gate, I have a question. How many possible timing arcs do we have here for an AND gate? Does anyone know the answer? Maybe put up some fingers. So I'm seeing 2, seeing 4 some places. 4? Yeah. So the answer is actually it is 4. So the way that you think about it is actually think about pairs of transitions between the inputs and the output ports. So in this case, there are 4 because both A and B are what's called positive unate with respect to Y, which means that for an AND gate, whenever you have a rising signal on A, it can potentially produce a rising Y. It can cause Y to rise. But it cannot cause Y to fall, right? So that's why it's called positive unate, because it's in the same direction. And so A falling can cause Y to fall, and then there's B rising. So here's all the possible timing arcs that exist for this particular gate. And I drew a timing diagram at the bottom, which shows what how you would actually see them inside of a real circuit. But the first one is if B is rising, you can have a rise transition on Y. A is falling, you can have a Y transition falling, et cetera. So then my question would be, for an XOR gate, how many possible timing arcs do we have to consider for this? Maybe show with a hand, or 2 hands maybe. How many? I'm seeing 8 back there. Yes, the answer is actually 8. So for an XOR gate, both A and B are non-unate with respect to Y, which means that basically depending on it kind of depends on both signals, right? And so a rise transition on A can lead to either a rise or a fall on the Y variable. Great, so that's combinational timing arcs. So these are basically all of the sort of timing transitions that you need to consider when you're doing static timing analysis. So now the next thing to think about is launch and capture, which are basically what are the start points and the end points. in your design, right? And so digital designs will typically have many inputs and outputs, and then they'll also have registers at which data is captured usually on the transition on a clock edge. So in this design that I have here, pretty simple design, how many start points do we see? Maybe people can put their hands up with the fingers. How many? So I'm seeing 3, 4 somewhere. Yeah, so clocks are typically not, they are start points, right? I'm going to not consider them start points for the purposes of this, though they are, you should be thinking about sort of the combinational delays of them as well. So here we have 3 start points, which are basically the data input, the start point from the first register, and then the start point from the second one. And then endpoints, so how many endpoints do we see here? Yeah, 3, that's right. So the endpoints are basically the data ports of the registers and then also the outputs here. All right, so setup and hold time are basically evaluated at the endpoints of all of the things. And these are basically requirements that you have on when, when a signal should arrive at a certain endpoint. And so setup time is basically the stable time required before the clock edge, right? So basically your signal needs to be stable before the clock goes high and captures the data, right? Makes sense. Hold time is the time required after the capture of the clock edge. And basically, registers have these requirements because they need to prevent metastability and make sure that they're capturing the data from the correct cycle. Violations can lead to, incorrect data capture. You might get one from a previous cycle, or you might get one from something that you're not expecting. Metastability is when you capture something that's rising at the time that you capture it, and it can cause basically a state where you have like oscillations inside of your flops. And basically, what static timing analysis is all about is about making sure you don't violate these requirements that exist in your design. So you have you basically want to calculate what is the fastest possible time it can reach, and like my signal can reach an endpoint. What's the slowest possible time? And so the fastest possible time will be your hold time constraint, and your slowest possible time will be your setup time constraint. And based on these static timing analysis, you can also calculate how much wiggle room you have. And so the wiggle room that you have for timing is called slack. And what you try to find in your, typically one thing you want to know is what is the worst negative slack in my design. So if I'm analyzing all the paths in my design, what is the worst negative slack? And that's basically your bottleneck, right? Because that's sort of what the maximum clock frequency that you can run at, for example, if you're considering setup time. Total negative slack is another useful concept, right? So often when you're iterating towards getting your design to meet timing, you want to consider your worst negative slack for all of the endpoints, right? So you basically, total negative slack is the sum across all of the endpoints in your design of the worst negative slack. And it's a very useful metric for kind of measuring timing convergence as you improve your design. So I'm going to do a quick timing analysis on that circuit that I showed earlier. We're going to do basically some assumptions on the input delays and output delays. And then I'm going to assume that all the timing arcs are the same. Inside of these, that's not a realistic assumption. Often you'll have asymmetric gates where they kind of have different timing arcs from different ports. The rise and the falls will be different. But for now, I'm just going to assume that these are all constant. So the first thing is we said that we had 3 endpoints. I'm going to look at first this endpoint, right, which is the first flop in the design. So what is the setup required time here? So the way to calculate it is you look at your clock period. So here our clock period is 3 nanoseconds, right? And then you basically, you also need to meet your setup constraint. So the setup constraint might add some additional timing requirement on top of that. So what you see is that you take your clock period and you subtract your setup time of the flop. And so then you get 2 nanoseconds required time. And then what's the arrival time? Well, it's just coming directly from an input here. So we have 1 nanosecond as that. And so here we have the requirement, the setup required time is met here for this particular flop. What about the hold required time here? So here, the hold constraint is that the signal needs to arrive after 0.5 nanoseconds, right? So starting from the beginning of the clock cycle, right? It's how long after. So 0.5 nanoseconds is the hold time. And we're successfully meeting that because we have the input delay of 1 nanosecond, assuming that that is correct. OK, so I'm going to skip the middle one, but let's talk about this output one, because this one has something interesting about it. So here, we have a clock period of 3 nanoseconds. And we have an output extra output delay, right, which is 1 nanosecond. So we subtract that out. And we have 2 nanosecond required time at the output. So the way that you calculate now the critical path, like whether or not we're going to meet this, is you try to find the longest path in this. And that actually ends up happening to be through, so from either this flop or the other flop, and going through 2 gates and then reaching the output. But unfortunately, in this case, we see that our signal is going to arrive. It's going to take 4.5 nanoseconds for it to arrive to the output through the gates here. And so you're actually, if you were to capture on the data out, you would see that you might get a signal from the previous cycle, which is not what you would expect. And so this is an example of a timing violation. And part of the goal of static timing analysis is to help you find them and resolve these, right? And you basically run static timing analysis throughout your chip design process, right? Both at the synthesis stage, you'll do it at the when you're various parts of your PNR flow. When you've done CTS, you need to consider like clock tree synthesis. You need to consider all of the stuff that comes with that, right? So there's a lot of skews and stuff that can be introduced. I won't talk about that in this talk, but yeah, if you're interested in that, maybe we can talk about it at the unconference tomorrow. Synopsys Design Constraints. OK, so I'm going to just go through the standard here really quickly, and what are the most important things to know about how to constrain your design. So the first is you want to be able to create clocks, right? And clocks are basically defined on certain pins, so you can define where they are. Sometimes you might have a generated clock, which comes from another clock, is derived from another one. And then the next thing is our input and output constraints. So these are really important that you make sure that these are set in your design. This is where you constrain a clock with respect, an input or an output with respect to a clock. And it's really important that you do this, because otherwise you might miss some certain timing paths that come from those inputs. And then finally, there are case analysis and timing exceptions. So case analysis is basically where you assume that, let's say you have some registers that are like CSRs, right, for maybe generated with peak RDL. And these are basically set to a particular constant value. That may have an impact on the timing. Maybe you would be too pessimistic if you didn't consider that those paths were constant. And so, yeah, that's just another thing to consider. And then false paths, this is basically where there's certain paths you want to ignore. Multi-cycles, where it might take more cycles to get there, et cetera. So I'm just going to talk quickly about how timing arcs are actually calculated. So the simplest is just the constant model, which I talked about earlier, which is just you assume the timing arcs are just a fixed number, doesn't matter at all what the inputs to the input signals are or what the output signals are going. This is typically pretty inaccurate, and it has to be very pessimistic for it to work. But people do use these, right? Sometimes these are used for like when you have a macro in a design, you might assume that, OK, I'm just going to use like a very pessimistic timing assumption on this just to be safe. So I've seen that used. Nonlinear delay model. So this is sort of the this is maybe used a lot more in the earlier submicrons, not the deep submicron. But basically, it's a lookup table. You have a lookup table that's a function. I'll talk about it a little bit more. But it shouldn't be used for sign-off. It's good for getting early timing estimates. And then there's CCS. So CCS is basically the sort of the state of the art. It's effectively a lookup table of a SPICE simulation where you actually capture all the waveforms that you need, and you just compute like it's a little bit more closer to almost dynamic timing analysis, I would say. So it's good, yeah. OK, so let's talk about NLDM. So NLDM is basically a 2D lookup. It's a 2D function, right? You have your delay. It's a function of the input slew, right, which is how fast the signal is rising on your input, and then also your output load cap, and then you also compute the next slew in the same way. But it doesn't account for some of the more complex things that you see in deep submicron, like Miller capacitance. And then, yeah, basically slew rates themselves, just like assuming you have a constant rise rate, is not really the full story. You need to have the full shape of the curve to calculate it accurately. And that's what CCS is. CCS basically just takes that and is able to capture like the exact waveforms that you see and then make the computation on the fly. The analogy that I like to use between NLDM and CCS is you're trying to predict how fast a bucket is filling up. And then NLDM is like, it takes 5 seconds when you fill the faucet set to medium. So it's like kind of, you don't have as much granularity into what it is. And then CCS is like, oh, here's the flow rate when you turn the faucet, and like shows you that. And then the second is obviously going to be much more accurate, especially when you have variations in the pipe pressure, the bucket size, or the faucet knob. All right. So OpenSTA, I'll just talk quickly about what it is and some of the other, there's a couple of other free and open source STA tools out there. So OpenSTA has actually been in development for probably the longest. It's been, I think, since either the late 90s or early 2000s, and was open sourced pretty recently. It's used by the Open Road project, so it gets a lot of issues filed to it from there. And then more recently, there's been ISTA. I think there was a talk yesterday from the Chinese folks. And this is used inside of the IEDA project. It's rapidly developing, but I would say the maturity and the speed right now is, from what I've seen, is lower than OpenSTA at this point. And then there's OpenTimer. This was one that was being developed. It seems like it's a little less maintained now, but has a very nice architecture for bolting it onto other tools. I would say probably the easiest one to bolt on. Yeah, and these are all designed to be, they're designed as either libraries or standalone tools. So you can use them either to analyze a design dynamically, or you can hook it into your tool using the APIs. Great, yeah, so OpenSTA commands, like basically the way you do it is you read your Liberty files, your libraries, you read your Verilog. This would be mostly like a netlist that you have. Your SDC, those are the constraints that I was talking about earlier, and then also parasitics. I didn't talk much about parasitics, but they're very important for deep submicron. And then the whole point of OpenSTA is to be able to report all of the problems in your design. So report checks is probably the most important command that you'll see inside of it. Report units will tell you the units for everything inside of your design, and then there's the TNS and WNS reporting. And you can also group paths into like different things if you're interested in like register to register paths only, et cetera. OK, I was going to give a demo. I don't know how much, do we have time for like a quick demo, or should I just show sort of the results? We're good at it? Awesome. OK, so let me try to do that. Let me see if I can pull. OK. So here I created a, it's actually the exact design that I showed earlier. It was that diagram. So let me pull up the diagram for it. Give me 1 second. So I think it was this circuit. Yeah, so it was this circuit. So I created this circuit inside of, this is basically the netlist for it. This is the SDC file. So basically all you need to do is you create, for example, the clock period. So you use create clock, give it a name. Sorry, I'll make this a little larger so you guys can see it. And then you set an input and output delay. If you don't do this, you'll see 0 paths. So you need to make sure that you have the ports constrained with respect to your clock. And then I also created a Liberty file. So I'll just show you guys what the inside of a Liberty file looks like in case you haven't seen it. But basically, this is where you define like what the cells are, what are all the timing arcs between them. So this is an AND gate. The input pins, you basically just define the capacitance, right? That's the load that the cell before it will see. And then for the Y pins, you have these timing blocks, which have, in this case, I'm just using the scalar model, right? Scalar is basically the constant one. But you basically have the timing arcs with respect to A rising and then A falling, right? And yeah, and so that's how you do this. And then the same thing with B. And so basically, the timing arcs are defined here. And then here's the script that we use. So basically, it's a bunch of like, I would say, all the types of like just loading in all of ingestion, and then also at the end we do basically like reporting stuff, right? So we can report exactly what we want. We use these report checks commands, and these will basically produce it. So when you run it, it's very fast. You just basically run, I think, let me see what I ran here. You can just run the tool, run it on your tickle script, right? And it will do exactly what you tell it to do. And at the end of the day, you get these reports, these nice timing reports. And these look very similar to what you would expect to see. So here we're seeing that our data is arriving at 4.5 and the required time was 2. And so there was a Slack violation here on that path that we saw. And so now we know that we need to go and fix this. We recently contributed upstream a JSON extension for this so that you can interface it with other tools that need to use the results of the STA for further processing. And yeah, so that's the quick demo. And yeah, I think that's roughly it. Yeah, so I'll just go back and talk about, so we've, at Silomate, I'm the CTO of Silomate, we have been upstreaming a lot of our contributions to the OpenSTA. We've done RTL source attribution, so that's basically the ability to see the original RTL line numbers that correspond to a particular cell. We have ways to get advanced SDC filter expressions that are supported by commercial tools, CentOS and RHEL 7 Docker file support, Brew file support, and then yeah, JSON reporting, and then also several minor bug fixes and performance improvements that we've seen. It's important to note, so I've seen that there's actually 2 repos. One of them is inside of the OpenRoad project. It's important that issues are not filed there because nobody's looking at it, and they will just get ignored forever. It should actually go upstream to the original repo, which is the Parallax software one. Yeah, OK, so that's basically it for the talk. There's a lot of really cool topics in STA that I didn't cover here. But if you're interested in any of these, please feel free to talk to me. Parasitics, very important. Of course, and then the models for calculating delays and stuff in deep submicron is very intricate and complex and very interesting. I'm happy to chat with you about it if you're interested. Library characterization, these are how Liberty files get created. They get created from SPICE simulations. Clock non-idealities, there's a lot of stuff that come in when the clock network comes into the picture. I didn't talk about those at all. But then, yeah, max load and max transition constraints, CDC, RDC, CCSN, there's like noise modeling stuff, and then corners. I didn't talk about corners at all, but those are very important as well. And thank you. And I also want to say that Silomate is hiring, so we're the co-pilot for chip designers. We love open source tools, so we love use and support them. And we're well funded, backed by Y Combinator. If anyone is looking for a job and interested in electronic design automation tools and improving the way that people design chips, come talk to us. Very happy to take it from there. Thank you.
Great talk, nice work.
Thank you.
I like it, it's good. STA is important.
I just have a question about doing tape outs in like 7 nanometer, 14 nanometer, because I have heard stories of people using OpenRoad to like, I don't know if they were successful or not. People just say that like I've used OpenRoad for 14 nanometer FinFET, and I wonder like, is it possible to get away with using NLDMs on some of these smaller process nodes?
I wouldn't recommend it for sign-off checks, just because they can just give numbers that are not what you would expect, right? And honestly, if you're using open source tools for silicon, I would leave a lot of wiggle room. I would make sure you have a lot of slack at the end of the day, rather than a little bit, because these aren't necessarily well qualified across hundreds of commercial users like the commercial tools are. So yeah, I would recommend, like at that point, if you're if you're leaving a lot of slack, it doesn't matter whether you use NLDM or CCS. But it probably makes sense to use CCS if you can. Yeah, if you have the libraries available for it.
Also, a quick follow-up: does OpenSTA support CCS and CCSN at the moment? And if not, are there like plans to implement that?
Yeah, it does support CCS, and CCSN is not supported. I would say even the CCS support is in beta. It kind of has a couple, and then CCS is actually calculated a little bit differently by different tools, which is kind of an interesting quirk of it. It's not like the way that interpolations are done, for example, is different across tools. And so there's a couple of different timing ways that it can get calculated inside of OpenSTA. You can pick which delay calculator you use. And yeah, and then CCSN is not supported. But yeah, so basically, yeah, I think there are plans to do it. But I'm just not sure where they're at right now. I think it's just not like the biggest priority.
Cool, thanks.
Of course.
Thanks for the talk. So, how much trust would you put in OpenSTA these days? Kind of there's, I mean, there's kind of the models you have available. Sure, that's one thing, but kind of, would you trust if you have the same models, kind of run them against a commercial tool? Do you expect to get the same outputs, or
yeah?
Did you see kind of discrepancies there before?
Yeah, I think it's pretty good. Actually, OpenSTA, I think the code base is used inside of some commercial like FPGA tools, for example. It's basically been licensed, like a commercial version of it, and so yeah, you can expect it to be pretty good and pretty close to what commercial tools say. I would say that for CCS, yeah, it's just computed. The problem is just that it's like computed in different ways across different tools. So you just have to be a little careful with that. And it's definitely in more beta support.
Yeah, couple of things. First of all, you didn't mention support for the rates.
Yeah, it is supported.
Okay.
Yeah, D rates are supported. Yeah.
And the second one is the difference between the STA that runs inside the PNR tools and the one run as sign-off is that the main usage model is you want to take it out and create timing scripts, timing ECOs. Is that anywhere supported in this flow, or is?
So like being able to create like a timing ECO it's not supported in OpenSTA. So OpenSTA is designed to be just the timing analysis engine and not do any. You can kind of instrument it, so it does have like commands for being able to swap out cells, for example, which might be how you do like part of how you do ECOs at least. But I would say that it's not really designed to be like do more than just the STA part on its own. You can you tack it onto other tools to do.
I just want to mention that the difference is open source versus proprietary. You can get a commercial support contract for OpenSTA from Precision Innovation. They'll quite happily sell you support and that type of stuff for OpenSTA. So even though OpenSTA is an open source tool, it's definitely a commercial tool as well.
Yes.
So.
That's quite good and not often done, I reckon.
Yes. I would say it's compared to most of the open source tools in the back end side, it's very mature, I would say, compared to all of them. It has basically full support for SDC, unlike some of the other tools like IEDA and OpenTimer, which is really great. So you can basically use it almost as a replacement for most like commercial STA tools if you'd like. And it actually runs very quickly too. I've done some benchmarking and it compares favorably to a lot of other tools.
Yeah, wow. Okay, we gotta call it there. Thanks,
All right,
Akash.
thank you.
Cheers.
Thanks, everyone.